let's graph these conic sections in polar form, and along the way we're going to be finding the eccentricity, the directrix as well. So the first thing to do is make sure that this is in standard form, which would look like this in this case. But we can tell it already is in standard form. We didn't have to do any rearranging. So that means that I can find the eccentricity first just by matching what I have on the left with what I have on the right. So E must be 1, which tells me that I'm looking at a parabola. So that's what I'll be sketching. And the directrix we can get by finding the K value. So we know that 4 must equal K times E, but we know that E is equal to 1. So K is equal to 4. Now careful, that's not the equation of the directrix in this case. Right? K is actually just a distance. And this is a cosine graph, which means we have a vertical directrix, and in this case it would be at -4, not +4. Okay, so now let's just sketch those in. Remember that the focus will always be, the focus is always going to be at the pole. So there's our focus. And we know that my directrix is at x equal to -4. So I'm just going to dash in my directrix. And now we got to get points on this parabola. So the best way to do that is just to make a table, and notice that we're dealing with a trig function there whose period is 2 pi. So we'll use those convenient values to get some good points and see if that ends up being consistent with the fact that we know we should be looking at a parabola. So let's make our table, theta values and r values. So 0, pi over 2, pi, 3 pi over 2, 2 pi. I guess if we need other points, we can deal with those when we get there. But and so I don't have to keep zooming out, I'm just going to copy that equation over here. Okay, when you plug in 0, you'll get 0 in the denominator because the cosine of 0 is 1. So there's no value there. And similarly, when you plug in 2 pi. And when you plug in pi over 2, cosine of pi over 2 is 0, so you get 4. When you plug in pi, you get a 2 in the denominator, since the cosine of pi is -1. So you get 4 over 2, which is 2. And when you plug in 3 pi over 2, again, cosine of 3 pi over 2 is 0, so you get 4 over 1 minus 0, which is 4. So let's plot these points in polar form. So pi over 2, 4. So rotate pi over 2, walk out 4. And rotate pi and walk out 2. Rotate 3 pi over 2 and walk out 4. So let's just check for consistency. First of all, we know this is supposed to be a parabola. We see that the distance between the focus and the vertex, which must be right here, right? This must be describing the vertex. That distance is 2. And the fact that when you rotate 0 or 2 pi, there is no point on the parabola makes sense if the parabola looks like this, which it should. Okay, so always doing a consistency check is not a bad idea. So there's our parabola in the polar form of our parabola. Let's do a couple more graphs. Okay, so here we have to graph this polar equation. Now before we do that, let's just make sure we can turn it into its standard form so we can find the eccentricity and the directrix. So the standard form in this case would have to look like this. Okay, so the first thing to notice is that there should be a 1 instead of a 5 beginning that expression in the denominator. So we need to rearrange that top equation to make it look like the one in standard form. So to do that, we need to divide the denominator and the numerator by 5. So now it is in standard form. And that tells me that E, the eccentricity, is equal to 3/5. And since that's less than 1, I know that I'm going to be graphing an ellipse. And to get the directrix, we just match it with what we see in the numerator. Now, the numerator should be expressed as k times e, so we know that 16/5 is equal to k times e, but we know that e is 3/5. So, if we just multiply both sides by 5/3, we get that k is equal to 16/3. And now looking at the overall structure of this ellipse, that really means that we need to write the directrix as, now it's a cosine, so it's going to be x equal to positive 16/3. Okay, so we got the eccentricity, we got the directrix, so now let's go make the graph. Sorry, that's not sticking with it, but we'll just deal with it. Okay, so I'm just going to copy it down again, the original version. So let's just first graph our directrix. That's happening at 16/3, which is a little more than 5. So 1, 2, 3, 4, 5. So somewhere around here. Again, our focus is going to be here at the pole. And now what I need are some points. So I'll make a table. And again, we can use our convenient values there. So we'll use 0, we'll use pi over 2, pi, 3 pi over 2, and 2 pi. So if you plug 0 in to our in for theta, you get r equal to 16 over 5 plus 3 times cosine of 0, which is 3 times 1. So it's 16 over 8, which is 2. Plugging in pi over 2 makes the cosine term go away, so you get 16/5. Plugging in pi makes it a negative 3, so it's 5 minus 3, which is 2. So 16 divided by 2 is 8. Plugging in 3 pi over 2 again makes the cosine go away, so you get 16/5 again. And plugging in 2 pi gives you the same thing as when you plugged in 0. So let's plot these points. We rotate 0 and walk out 2. We rotate pi over 2 and walk out a little more than 3, right? Because 16/5 is like a little more than 3. We rotate pi and walk out 8. We rotate 3 pi over 2 and walk out again a little more than 3. And that's it. So it doesn't look like we've got, enough scaffolding for a nice ellipse, but we can start making sense of this by using what we know about an ellipse. So one thing we know about an ellipse is that the distance from the focus to the vertex, when we already know one vertex is here, the distance from the focus to the vertex is 2, which means that my other focus must be over here. So that's focus 2. And then also the way that ellipses behave in terms of their symmetry, if to get the vertical distance from the first focus to a point on the ellipse is plus or minus 16/5. Well, that's going to be the same for my second focus. So now you can see we got 6 good points, and I can sketch my ellipse. And let's finish with one more graph here. So again, the first thing to do is make sure you can match it to its standard form. So the standard form for this one would be r equals ke divided by 1 plus e sine of theta. And again, that 3 down there in the denominator should be a 1. So I need to do a little maneuvering here. So I'm going to divide the top and the bottom by 3. Okay, and so doing that tells me that my eccentricity is equal to 5/3, which is bigger than 1, so I'm going to be sketching a hyperbola. And then since ke is supposed to be 16/3, and we know that e is equal to 5/3, we can find k. So multiplying both sides by 3/5 will give me that k is 16/5. But the actual equation of my directrix, therefore, would be y equal to, now that's a plus, it's in the form of plus e sine theta, so it's going to be y equal to positive 16/5. Now the one thing you got to keep in mind is that this is a hyperbola, so it will have it's going to actually have two directrixes, but we'll deal with that when we get to it, and we can just use symmetry to find it. So now we want to graph. So the first line of business is to get some good points. So we'll make our standard table. I'm going to get rid of this here. So I'm going to make my standard table here. I'm going to sketch in my directrix right away, so that's located at about 3 1/5. So a little more than 3. So it's y equals that, so it's this horizontal line. So this is y equals 16/5. Okay, and I know one of my foci is here. Okay, so, and I'll just copy down my equation down here so that we can refer to it. So the equation is r equal to, and again I always go back to the original for evaluating because I think it's just easier not to deal with fractions. So you plug in 0, you get 16/3. Plug in pi over 2, you get 16/8, which is 2. Plug in pi, you also get 16/3. Plug in 3 pi over 2, you get -8. And you plug in 2 pi, you get 16/3 again. So let's plot these points. I'm going to do them in red. So when you rotate 0, you walk out 16/3. So that's, 5 1/3, so a little more than 5. Okay, and then when you rotate pi over 2, you walk out 2. And when you rotate pi, you walk out 16/3 again. And when you walk out 3 pi over 2, you walk out -8, so you walk backwards 8. So that would plot this point. Okay, so what we have here is, and then when you rotate 2 pi, you're back to where you began. We found one arm of this hyperbola. Here it is. Okay, and here's a vertex, or a vertice, a vertex. There's a vertex. This is the other vertex. Now we're going to use symmetry to get the rest of this. Okay, so how do we do that? Well, let's note the distance between this first vertex and the directrix. Right, the vertex here is at 0, 2. If we think of it in the Cartesian system. And this directrix is at 3 1/5. So I'm just going to note distance. I'll put it in blue. This distance here in blue we'll call that D. This distance is equal to 3 1/5 minus 2, which is 1 1/5. So if I just go 1 1/5 away downwards from my second vertex, then I'll get my next directrix. So if I take 8 and minus 1 1/5, I've got 6 4/5. So there's my second directrix here at 6 4/5. So that's roughly, somewhere here. Okay, and then let's just notice that the distance between one of these points here, let's call this here point P, the distance between point P and the directrix is 16/5. And also that if I wanted to plot the second focus, I could go the same distance from the vertex to the focus. So combining those ideas, I can get everything. So from the focus to the vertex is 2. So if I just go up 2, I'll get my second focus. And those other 2 points lie on the same horizontal line as that first focus. So I can just mirror those points there. I guess it doesn't have to be perfect. I think at this point we just want an overall decent sketch. So I'm just mirroring the distance. I'm just trying to put these points in the same horizontal line as that focus to get the other 2 points of this hyperbola. Okay, so there's our graph, and that finishes up, that concludes our graphs of conics in polar form.